on Zoom, and now we should be also live on Facebook. So I think we're good to go.
Good to go. Excellent. Well, hello, everybody. We are live on Zoom again and live on Facebook. Managed to get that working this week, which is great. And this is our weekly sessions going through the modules of what's in the Unified Science program at the Resonance Academy. And this is week 4 of our 6-week overview of the program. And again, my name is Marshall Lefferts, a member of the faculty and of the board of directors. And I'm here with Nassim Haramein, who's our SF's founder and director of research. And today we also have William Brown, who is our resident biophysicist. And today's topic is unified physics, which is kind of the heart and core of what the science is about within the research that Nassim's been doing for 30 years, and with William and Olivier that we had last week, and many others advancing this theory of unified physics that is really proving to answer many of the questions in physics that have not been able to be answered. So welcome everybody on Zoom and on Facebook. And I just wanted to say before we start that I noticed that some people in the past sessions have been asking, where's the material? I don't know where the material is. I just see the webinars. And so if you're new to the program, all you have to do is go to resonancescience.org. And there you can sign up for the course, the Unified Science course, for free. And in there is the 6 modules that we are going through over these 6 weeks. And so we are in the 4th week of these live webinars. And as I said, today is going to be covering module 4 of unified physics. And before we dive into that, I just want to welcome Nassim to say hello and give a little, whatever you want to say to welcome everybody, Nassim.
Hi, everybody. It's great to do this again. And yeah, like Marshall was saying, you know, when you register for the course, which is free, then you'll have a little button on top with my courses, and in there will be the Unified Science course that you will be able to go through the 6 modules. And yeah, we're excited to have some 20,000 people taking the course right now, or close to it, and and the participation in the forum is great. I wish I had more time to jump in there. I'm gonna make some time and jump in there hopefully next week, or maybe at the end of this week, and talk with people. But it's remarkable, it's fun, and we're all learning together. And I'm working some information that needs updating on module 6, and I'm starting to think about updating this module here, module 4 that we're doing today, which is the Unified Science module, because so much more has been discovered since almost 7 years when this module was written. And I'll try to kind of fill that in on this session as well, a little bit, for people, so they understand a little bit of the details that are supporting what's in the module 4, which discusses the holographic mass solution, and where it has gone since 7 years is a very long way. So I'm excited to be able to share that with everybody today.
Yeah, great. It's exciting to get to this point in our series here, to really talk about the unified physics theory itself, which we've been leading up towards all this time.
Yeah, and you know, it's the other side of the Great Wall of module 4, of module 3, which, you know, people have described that way, which is the standard,
right.
the standard model.
Yeah, The firewall.
The firewall.
The event horizon.
Yeah.
Right. Well, I'm going to just share my screen quickly and give everybody a little bit of a look at this module and the contents in it.
I better not cough on my computer because you might take off.
Yeah, none of that. Right. Put your mask on.
Catch a virus.
So this is inside the course now. As Nassim said, if you go to my courses, you'll see everything. Looks like mine is not loading now.
Yeah, it's right there.
There it goes. Great. So you'll see these are the various courses that I have enrollment in, including one of the electives here, and then the modules for each of the 6 modules of the Unified Science course. Here's module 4. And as Nassim mentioned, also there's the forum over here, which you can go into and pose questions and have conversations with people that are participating in the program and faculty, and it's a great place to share thoughts and ideas and questions. So going into module 4, there we go. This doesn't want to scroll too well. Here we go. So as usual, there's an introductory video, but the main sections of this module, first of all, introduce the unified physics as a whole. And what is unified physics? What are the big unsolved problems in physics? The holographic universe, the fractal universe, black holes. These are like the core principles that are underlying the theory, which is very important to understand as the context for going deeper into the theory. Then it goes into space, because space is where it's at. This theory, well, it's everywhere, really, whether it's in space or matter, it's all one and the same thing. But really the kind of the primary context for understanding the theory is to understand the nature of space itself, and space as both being 99.999% empty, although we know it's not actually empty, it's actually filled with energy, and it's quantized, as in this section here, dividing space-time, quantization. And that's another key aspect of understanding the foundations of this theory. And then it goes into quantum gravity, which is very much based on the research and the paper that Nassim released in 2012, Quantum Gravity and the Holographic Mass, and then papers subsequent to that as well, describing the nature of gravity, both at the cosmological scale as well as at the quantum scale, at the atomic and nuclear scale, and how really it's all one and the same again, but really defining how that is occurring at the atomic scale and at the quantum scale. Then going into the confining force, which is also known as the strong force in nuclear physics, atomic physics, and again showing how that force is directly associated with the quantized gravitational effects. And then discussing the connected universe, the holographic network of space-time, entanglement, the whole universe is a black hole, why that perspective appears to be true, experiencing the unified network, fundamental harmonics of the Planck scale. I know you touched into some of that, I think last week, Nassim, a little bit.
Mm-hmm.
The large number hypothesis, you did talk a bit about that last week.
Mm-hmm.
Cosmogenesis, continuous creation model, and then into the geometry and spin, the torus, the origin of spin, the geometry of space-time, etc. There's a rich amount of information in here that is presented in an overall user-friendly manner, with enough of the technical aspects and equations in there for those who are capable of really studying those to really get to see how what it's really founded on mathematically. So that's a quick little overview.
Yep.
Where would you like to begin with discussing this today, Nassim?
Well, we could start with some of the initial concepts. Okay, so clearly the divergence, as we kind of elucidated in the earlier module, mostly module 3, is where the structure of space was idealized to a mathematical model called space-time, and the ether was removed, or the physicality of space was removed. So all of a sudden, space could curve, produce gravitational fields, but was not made of anything. It was just a mathematical model, as if you have a mathematical model that gives you the right answer for very precise, orbitals, for instance, the orbital of Mercury and other things. And the resulting force that you're calculating is dissociated from the physicality of space, as if space could curve but not be physical. So that was the divergence. This is where it happens, and that's why this starts with understanding that space is not empty but full, and that's a really important concept, and that the fullness of space produces effects that are not just gravitational. That is, it curves and produces gravity, and as well, it produces electromagnetic interactions, because it is the fullness of space is as well the oscillation of space. That is, what is filling the space is electromagnetic fluctuations, like radio waves, microwaves, all kinds of things that are in the space, right now, that you don't know are there, that you don't feel unless, they are in the range of your senses, which is a very, very, very small range compared to what's in there. Otherwise, if you felt all the stuff that's in there, you'd be in trouble between infrared and ultraviolet and gamma rays and background radiation from the universe. There would be a lot of noise, including all the radio stations. And so you kind of probably would get put in a large institution with padded walls, pretty quickly. So basically, there is as well these electromagnetic fluctuation that are very, very, very fine, very, very granular, and that fluctuates the space. And so those very fine fluctuations are the structure of what Einstein described as space-time. And from understanding this, you can start to understand that these electromagnetic fluctuations, when they're coherent, when they're in resonance because of self-organizing or co-moving systems, meaning, like, imagine that there is this sea of electromagnetic fluctuation, but there's regions where they're coherent because there's angular momentum, there's spin in that region, right? That the particles can all spin together, all the photons are spinning together in a ball, if you'd like. That in those regions, then you have electromagnetic radiation that we call protons, electrons, lepton, all kinds of stuff that we have this found to be what we call our reality, which is mostly made out of space, 99.9999. So there's a little radiation that's produced by the space when it's coherent in the region, and we call that reality. And the caveat is that these little bits of information that makes up, or these little particles that makes up the structure of space, we could call it a Planck plasma. You know, those particles, they can be thought as information. And so basically, as information is, you know, exchanging or moving in the space, it produces our reality, and eventually self-organizing systems, because there's feedback in these fluids and this information, and the self-organizing systems eventually have enough information that they can become self-aware, hopefully. And this self-awareness might realize that it's in the field, but it wouldn't be the first, you know, tendency. They would tend to think that they're independent from the field, since the field is at a resolution that's so far from the senses of this, you know, organized structure of space we call biology. But that's at a completely different scale than the fundamental field of information. So it doesn't know. And then eventually it realizes that it is. And that's when it unifies physics.
Yeah. Well, that's a great kind of overview of the context of how space and the dynamics of the movement and the spin of space create the density gradients and the forces. And I wonder if it'd be good to lay a little more foundation along those lines, as it does in the beginning of this module, and talk a little bit about the holographic and the fractal aspects that are obviously intimately correlated to what you just were describing.
Right. Well, you know, okay, so it's basically like a fish that realizes it's in water, right? It wouldn't be obvious at first because there's water everywhere, and it's just part of, you know, what the fish could think of as space. And it's not obvious that, you know, there's water. And initially the fish didn't think there was water, but then eventually the fish realized there was water, right? And in this case, a little bit like the analogy, if you could push the analogy a little further, you could say that the fish realized that the stuff that it sees in the water, like the reef and the coral and the other fish and all this stuff, is actually just coherent water, which it pretty well is. It's a little bit of minerals and water, you know, that are interacting, you know, to make biological life, for instance, like the other fish, right? And that, you know, in that water, there's the things it sees in the water are basically the water spinning, you know, in a coherent place where the water usually is not, you know, around the fish. But when it's something, if the fish had a really good microscope, it would see that it's the space spinning that makes up the little bits that makes up the other fish, and that makes up the coral reef, and that makes up, it's like little vortex of the water, right? In this case, it would be little vortices of the space, right? That makes up the electromagnetic field that we call atoms. You know, when you look at an atom, first of all, it's mostly made out of space, 99.9999, but as well, all you can describe there, all you can say about this thing you're looking at is that there's an electrostatic field in that region that makes it so it bumps against other electromagnetic field or electrostatic field. And these interaction, you know, makes up the material you see. So basically, you know, when we look at the proton, we don't see a billiard ball. When we look at an electron, we don't see a billiard ball. We just see an electrostatic boundary. we know it's a charge boundary. That's how we call it, you know, because it's not a thing. It's a division of the space. So then if you know that the space is full of electromagnetic fields that are fluctuating way smaller than the, you know, the atomic scale, the Planck scale, you can start to think, well, actually, there's a good chance that that electrostatic field is the result of the interaction that are occurring in the electromagnetic field at the lower scale, right? That what you're seeing is like a residual effect of the dynamic that's happening below in the water, for the fish example, where the vortex is, right? And you can see, you can imagine that in a superfluid kind of structure, or in the water, you know, the small vortex would engender larger vortex because things would be spinning together, and that would engender larger vortexes that make spin, you know, these things spin together, and that, like, you know, you get larger and larger vortices. And that's what we see, you know, we see like very strong vortices we call stars. We see very strong vortices we call galaxies, you know, clusters, superclusters. We see things are spinning into this dynamic at all the scales. And you know, when Maxwell wrote his equations for the electromagnetic field, he wrote them with an ether, and he spun the ether in vortices and put little billiard balls to describe particles in the vortices. That was the mathematical model that, you know, illuminated humanity on the electromagnetic field and its behavior. And it was correct, you know. So it was linearized later on by heavyweight and put into, you know, vector calculus. However, initially it was not, and it was a fluid dynamic of the ether that produced the electromagnetic field. So you can imagine that, so you get scales, but as well you get, if you think of all these little bits, since there's a lot of them, you get, and you can, and this is where the holographic mass solution comes in, you know, you can describe how much information in the electromagnetic field is being exchanged, how much is going out and how much is being absorbed by each boundaries, right? In like the little vortices, right? There's stuff going out in the vortex, right? Because of centrifugal force, and there's stuff falling in because of centrifugal force, right? So you can start, and I'm talking very generally, right? This is formalized now in our equation. But you know, you can think of it as like this smoothie of information that's going on, right? And that smoothie of information is exchanging with this field. And because this field, this is something people don't know. And, you know, it actually never occurred to me until I saw a little, I mean, it occurred to me a long time ago, and then I forgot to mention it later on, and then it just was reminded. This is like in the early time in the van when I studied for 5 years, isolated, and I was studying Einstein-Rosen bridges, which are wormholes, and the Schwarzschild solution to such wormholes. And I had forgotten that it was initially written as solutions for quantum mechanics, that is, trying to describe particles interaction like two protons as mini wormholes. And so I'm mentioning this because it's really important that people understand this is not completely divulge of what the mainstream has been thinking. It's not completely outside the track. It's very, very close. It's just that even some of our best physicists were unsuccessful in conveying, you know, very important things in their discoveries. Some being even Einstein or Rosen or you know, other examples, you know, for instance, Bohm and others, you know, that were not able to convey so, and that leads me to the holographic part. So it's exchanging information. These little vortices, the reason I jumped to wormholes, these little vortices in this fluid, this is a special fluid. It's not like water completely. It's in a different phase. And so it's a special fluid. This fluid is spinning. So you can imagine spin making vortices, and then imagine vortices connecting, you know, and then all of a sudden you have what we would call in using Einstein's equation, a Einstein-Rosen bridge. You have in space-time, now you have two regions of space that are not contiguous, you know, connected through a tunnel. And so imagine these tunnels, they're not just hanging out in space somewhere. They're actually at the very, very fine grain of space-time, like the little oscillations of space-time. They're little vortices like that, you know, that are tunneling, but they're spinning super fast. They're spinning at the speed of light. So when they tunnel, they make very, very, very thin and very, very long tunnels. And so that means that whenever the information is moving in the field anywhere across any of the boundaries, right, at any scale in the fractal of all the vertices, all the other vertices, because they're all embedded, are affected, right? Because it's an information flow across the whole thing, right? So that is holographic. And, you know, and it's was first formulated in the mainstream by the holographic principle, where they discovered, wow, if we count the little vortices on the surface of a black hole, the little Planck oscillators, which they made to the, one of the innovation I brought in was that I made it a sphere, right? And as a first approximation, a little sphere spinning at the speed of light, right? And so I imagine, but they counted the pixels on the surface of a black hole, and they found it to be equivalent to a quarter of the temperature of the black hole, or the entropy of the black hole. And that would, you know, not a quarter of the temperature. It, you know, the pixelation, a quarter of the pixelation give, you know, the temperature. And so basically, there is a direct relationship to the entropic and information paradox problem. And so it became very popular because all of a sudden they could say information doesn't disappear. It stays on the surface of the holographic black hole. And they start to think that the universe is just a holographic projection of a 2D surface. Well, you know, I had come to the same conclusion from another perspective, but from where I was coming, I was not just counting the Plancks on the surface, I was counting the Plancks inside the volume, right? Which I published earlier in the Schwarzschild proton paper that was so controversial. And so, you know, as I did so, I realized there was a relationship between the volume and the surface. As the little wormhole information, imagine the wormhole connecting the surface to all the other protons in the universe. There's 10 to the 40th on the surface. That's a huge number, okay? And it's 10 to the 80th atoms and protons in the universe. So, you know, 10 to the 40th is already a huge number, but remember the exponential. So 10 to the 40th is not half of 10 to the 80th, right? So imagine the 10 to the 40th little wormhole connecting to 10 to the 40th other atoms, right? And then the 10 to the 40th of those connecting to 10 to the 40th again. And now you have the, you know, the protons of the universe. But so now you start to get the sense of the fractal nature of the thing, right? Like it's got, you know, the information is going through boundary conditions, and you basically start to relate the holographic principle with the scale relationship in the universe and see that it's basically just information going through the scales, you know, that produces everything we see in the universe. And now you can start to solve very fundamental equation about physics, and they come out right. So, you know, just to finish on this, because it's the introduction, the result is like predictions you can make, and some of those predictions were made and were successful. One of them being the radius, the proton being 4% smaller than predicted by the mainstream, which is huge in quantum mechanics. 4% is huge. Okay, usually we're talking about like precision with some, you know, 10 to 14 digits, right? So like if you're off by 4%, the precision is gone to, you know, I'm not gonna say what, right? And so, you know, a 4% smaller radius, the proton, you know, messes with other fundamental constants in the standard model that doesn't make it very happy at all. And so, you know, if it was a change of only a few digits on the end of the radius, the proton, it could pass, right? But 4% is not even close to that, right? So, that was a big problem in physics when it was first measured. After I published and predicted it, it was measured in 2013 for the first time with muonic. And so this module will not have the information I'm just telling you. I mean, it will have the information about the early tests that were done, but not the later test that was done. So the first test was at the Paul Scherard Proton Accelerator in Zurich, Switzerland, where they were firing muons at protons to measure their radius. And, you know, the radius they measured all of a sudden was 4% smaller. And my prediction was inside the margin of error of their instrument. So it was good chance that it was more precise than the measurement still. And so that was just unacceptable to the scientific community at the time. There was all sorts of uproar, all sorts of patches were proposed to try to patch the model and, you know, account for this 4%. Many were saying, oh, they're using muons to collide with the proton. Muons are heavy electrons. Maybe they're flexing the surface of the, you know, electrostatic charge radius of the proton. And, you know, all kinds of models were proposed. So it wasn't confirmed until 2018. Well, there was multiple muon experiments that were done to continue to try to find a different result, because it was important to find a different result, but they kept on finding the same result. So then, you know, they finally got to a place where they had an instrument, or they built an instrument that cost quite a bit of money, but more precise, but as well to use normal electrons like they were doing before. But as well, they decided, while they realized that actually the problem might have been the rectification that the standard model of physics, the model that's more prominent, the change that the standard model of physics make to the measurement equations when they measure the, you know, radius of the proton, they included a modification that comes from the standard model and that plugs in for them to like make the calculation for the radius of the proton. they realized if they removed that, they got the same radius, and that it was it was much cleaner as far as the calculation, and it looked much more correct, and which resulted in the 2019 acceptance of this new value by CODATA, which is huge. That is the value given to all physics for the radius, the proton. All physicists, like, this is the standard value now. So it's been changed in history to this predicted radius. So that's not in this module, because the module was written 7 years ago.
Mm-hmm. We'll get to updating that sometime soon.
Yeah.
Before we go on, I want to say to the participants in Zoom here, I noticed there's a lot of chat, which is always great, and I noticed that there's an option to either send your chat to all panelists, which would be myself and Nassim and the others who are panelists, or to all panelists and attendees. And you want to make sure you're sending to the second one, all panelists and attendees, so everybody can see your chat posts. So those of you who, well, just check it out. You'll see if you're sending to only panelists, then only we're seeing your chat, and I'm sure you want to have everybody else see it as well. So check that out. So great, Nassim. That really gave us a good sense of the relationship between the fractal scaling of the density gradients, the vortices within vortices, the communication throughout the whole system of the energy dynamics and the informational aspects, and then the deeply, intimately connected nature through these little micro wormholes to how the whole thing is structured in such a way that the information is really present throughout the whole structure.
Yeah.
In a constant feedback loop. I was thinking it would be good to talk a little bit about the importance of the quantization aspect of this, because that also is key to how your theory is then being able to be applied at all scales, and even really defining the harmonic nature of the boundary conditions throughout all scales. And so if you could talk about the quantized nature of space itself and why that's important, that would be great.
Yeah, sure. And so basically, usually in the standard model, when you're talking about quantized space, which is, something that never used to be talked about because it was voodoo, space, as far as Einstein field equations is smooth, and at the, and somehow was never attached to the atomic level, which is quantized, so, and that was the divergence in physics. Relativity didn't agree with quantum theory, but more and more people started talking about quantized space, in certain theories, and certainly with people like, me and others, that now includes Frank Wilczek, Nobel Prize winner in physics, that have been trying to bring back the ether. We talked about quantized space, but not just at the quantum level. That is the quanta at the very fine level of space produce other quanta, other larger divisions, right, that go from the very small to the very big. And so it was important after this first success of the holographic mass solution that it would be successful at describing and predicting other values, like in our universe, that are larger quantas of the same equation. And so, the initial equation already accounted for all black holes in the universe, meaning it's an analog to Einstein's solution, Einstein field equation solution, the Schwarzschild solution. That is, you can take the holographic mass solution for a black hole, or you can take, the Schwarzschild solution. They will give you the same answer, except in the quantized solution, all of a sudden space-time is quantized, right? That's at the granular level, it's very, very quantized, and it's making other boundaries at the cosmological level we call black holes. And so now space is quantized, and the values that are in the holographic mass solution, like mass and gravity and all this stuff, are in the Schwarzschild solution. But in the Schwarzschild solution, it doesn't tell you anything about the physicality of the space that you're curving, wherein the holographic mass solution tells you what it's made of. And it's telling you that it's making boundaries because that's what it solves for the radius of a black hole or the mass of the black hole. And so you can take that and extrapolate it. So we extrapolated to the universe. Does it give the right answer? Yes, it does. It gives the right answer. Wow. It gives the right answer for its mass and for its radius. And one of the reasons it does is because the universe obeys exactly, like precisely, the relationship between radius and mass of a black hole. So a scientist that tells you, no, that's not true, the universe would be much smaller, has not considered that in the standard model, they have to add dark energy and dark matter in their equation to get the right mass for the universe. So when you put it all together, which is called the critical density or the critical mass, when you put it all together, baryonic matter that they have in the standard model, that is all the matter, and then, dark energy, which they have to add to all the galaxies, to make them do what they're doing. They do because their equation is deficient 80% the mass of the galaxy, and dark energy, which accounts for, like between dark matter and dark energy, 94% of the mass of the universe that they're missing in their equation. They're kind of little deficient in their equation, right? When they add that, then guess what? The universe obeys the exact condition of a black hole, but exact, right? And then, the equation now, this is not going to be in the module, is giving the right temperature, is giving the right acceleration, the right age, and so now you got the universe. And we've published this, and then we published it in very good peer-reviewed journals. Okay, well, at least like good enough for the amount of censoring I'm under, and definitely, publish as well the paper since then for the electron. And I think I mentioned both of those in the module, but not explicitly, and just wanting to say this has been published and peer reviewed now. And so for the model of the electron, the electron comes out just right as well, with a coefficient of alpha that goes in there. Alpha, which is this value that, like, is like magical in physics. You just throw it in, and it gives the right answer. Well, we find that it is a fundamental pattern of the universe at all scales from then. But basically, the holographic mass solution gives the right mass for the electron and its radius. And now we've extrapolated the equation with the help of Olivier Alirol. And Olivier is on the call today, so we'll get him on, and so is William. And so basically, we've been able to scale the whole thing to fill up the stuff between the universe and the electron So now we have stars, we have galaxies, we have clusters, superclusters, the whole thing. And we're drilling down into the proton, and we are getting all the subatomic particles, and we're getting, down to the Planck. But of course, we as well have been able to extrapolate sub-Plancks that are moving at 10 to the 40th faster than the speed of light in terms of their information transfer. So that's how fast the information is going through the wormholes. That's how fast you can go from one side of the universe to the other, when you go to the sub-Planck level. But you can imagine that our universe is in a larger one and in a larger one, and this equation gets us the possibility of calculating these things, and all of a sudden we have a unified view of physics.
Mm-hmm.
And science in general, because biology comes along, doesn't it, William?
It's actually module 4. They provided most of the information that I needed to understand some of the last little pieces that were vexing me to understand biology. Linking in the concepts of the space-time geometry, that was really key for me to better understand, but complete, for me, a picture of the biological system, namely those little micro wormholes. That was one of the key insights. It's definitely the unified physics goes right on through to a unified science.
Right. Both for biology, chemistry, even consciousness studies, right? And source of life, source of self-organization, planetary systems, it goes on.
So Nassim, with this quantized aspect, this nature of the universe, the space being quantized, as you're describing it, it's the scaling relationships of that quantization that we are really studying in physics. Especially what we can observe is manifestation of the scaling of the quantized relationships in the spin dynamics of the spatial field. And the next step in the progression of understanding how this all relates then is to tie that into gravity and the quantization of gravity. And and that is also, I know it's a theory that has been proposed by numerous researchers over the years in different ways of approaching it. And so why don't we just have you just describe a little bit about how that actually works, and not only as gravity at the cosmological scale, but then at the quantum scale as well, to show that really there's just one dynamic at play here, and it's due to this quantized nature and the scaling of that and the density gradients that we have these, what we call different forces, but they're really the same thing. So maybe we could talk about that a little bit.
Yeah. So I mean, that was the impetus of my paper on the Schwarzschild proton. It was the the initial calculation, which was really back of the envelope, and I threw in that paper because initially I threw it into the scaling paper I wrote with Dr. Walsher, and then I did a paper specifically on it after. And then when I did the paper, I was more specific about my calculation, but it was still very initial. And that was that if you took 2 protons and you calculated the amount of energy inside them, not just their rest mass, in terms of the vacuum fluctuation, as I was saying earlier, eventually you realize, wow, the thing I'm seeing is actually the result of smaller things that are all spinning together, right? So I calculated the energy of those smaller things, and I realized it obeyed the proton obeyed the condition of a black hole, you know, very well. And the mass that was missing, other than the rest mass, to make it a black hole was a gravitational effect that we call the strong force. That is, the energy I was missing for the proton to be called a black hole was exactly, not approximately, exactly equivalent to the strong force. And that just could not be a coincidence. And the standard model doesn't have a source for the strong force. And so that was my first attempt at the equation, which was back of the envelope. And then in the holographic mass solution, I showed how this force of gravity that we call the strong force has a much shorter range, you know, than the gravity we see at the larger scale, not because it's something completely different, it's just because there is what's called a Lorentz effect, which is basically that, as Einstein discovered, space and time is relative. And so when you have an acceleration towards the speed of light, mass increase, right? And time slows down, right? Like, so that, you know, the length of an object gets shorter and, you know, more massive as it approaches the speed of light, and it gets, you know, slower, meaning it appears to freeze in time for you from an external frame of reference. So this Lorentz contraction is what I included in the equation to show that really gravity. So imagine you have all these Plancks spinning, right? And you can imagine that it's entraining the Plancks in its vicinity a little bit. That's called frame dragging in space-time. And you can think of like, well, when it's dragging, right? Basically, if the proton, if you look at the energy of the surface only, you're going to get the rest mass. But if you look at the energy of the effect on space-time around it, you have to include that in your mass calculation, and then you get a black hole. So, and we know it's spinning at near the speed of light. So this give me a mathematical way to show that the force would be very short range, very close to the horizon of the proton, but would drop very, very rapidly to the force of gravity that we see further away from the horizon of a black hole. That there's a very sharp, you know, curve, you know, exponential curve close, because the object is gaining so much weight from spinning near the speed of light, if you'd like. And, you know, when you look further and further from it, then that force, right? That force becomes weaker. Gravity becomes weaker. And it's the gravity we measure, you know. So it's not two forces, it's the same force acting differently depending of the circumstance it's in. And then the equation that I came up when I solved the holographic mass solution is that, oh, and by the way, this curvature is not just some, you know, computational model of space-time. It's actually the fluids of space-time, the Planck field, you know, interacting between the outside and the inside of the structure, meaning like all the spinning, you know, the vortex of little Plancks that are going are actually affecting the boundary near it. And remember, there's stuff going out, there's stuff coming in. And so as stuff goes out and comes in, it produces an energy event. And that energy event is the standard mass of the proton. So I calculated if that was true, and it turned out to be true. And it turned, but only if the radius was 4% smaller. Mm-hmm. And so I predicted a 4% smaller radius, which we just went through, which was confirmed. So basically, the model came together to show that gravity is not always weak. Of course, gravity is extremely strong at the event horizon of a black hole, right? At the surface of a black hole. And so and in that case, it has a different reach. And that's why they had started the strong force, because they couldn't figure out why the strong force had such a different curve of interaction than the gravitational force, which has a much longer, distance of interaction. So this is why the two are related. And so then you have fractal gravity, because you can start to think, from the holographic mass solution, you can extrapolate to planets and stars and galaxies and all this, and you end up getting the right answers. You're getting the right masses. You don't need dark matter. You don't need dark energy. You don't have to fudge anything. It all comes out naturally. So it's correct, right? Because you can confirm it at all these other scales.
Mm-hmm. And you were just mentioning you don't need dark matter, you don't need dark energy, because it's those things are, the names are trying to describe, which they don't actually have any description for, and have not been able to experimentally detect whatsoever, are accommodated, they're accounted for because of the quantized nature that you're just describing, and how the gravitational force and the interaction of all the protons combine, and then the space itself actually co-moving and co-rotating with a galaxy or a star or a planet.
Right. If you
accounts for
that part, yeah, exactly. Just like the proton, if you calculate that part, that's co-rotating, right? The space itself co-rotating. Now you get the right mass for the galaxy, right? Because it's not just the matter in the galaxy, it's the stuff that makes the matter do its thing, just like
quantum space.
Yeah, it's like if you were to try to calculate the mass of the cream in your coffee in the morning, right? And so you see the cream spinning, right? You see the cream spinning, and you're calculating how much cream there is, like the energy of the system, by just calculating the movement of the things you see, but you don't consider the coffee. You forget to include the coffee, right? The coffee is what's entraining the whole thing, right? Like if your coffee is black in the morning, you spin it, you take the spoon out, you can't tell it's spinning. If it's a good black coffee, you can't tell it's spinning until you put the cream, and then it makes a little galaxy, right? Well, you can't account for that galaxy without the coffee. The coffee is really important. If you're going to try to account for what you're seeing, you got to include the coffee, right? Because that's the energizing part, right? Literally, if you drink it, it does a pretty good job. So basically, it's the same thing for galaxies, and it's the same thing for the universe. You got to include the fullness of space in the mass calculation of your universe, so that it gives you the correct mass for the universe. They miss those 2 points. So of course, they're missing 94% the mass of the universe, and they can't find dark matter with all their attempts and 2 decades and billions of dollars. And of course they can't find it, because it's not particles of matter you can't see. It's actually the structure of space, and it is particles that you can't see. They're at the Planck scale. So to measure them would require Planck scale experiments, which we don't have, at this point, either than the Casimir effect that tells you the space is full, but you can't literally measure the particle that fills it.
Yeah, great.
It's just too small.
I just want to, I was reminded to mention to the participants here on Zoom, there is a Q&A button, and some people are putting questions and good questions into the chat, which go and disappear, and to be able to track them. So if you want to put a question in the Q&A that's related to what Nassim's talking about, to the unified physics topic here, please go ahead and do so there. We have a whole bunch already. We're not going to ever get to all of them. We never do, but we'll get to what we can do. But last thing, I think, Nassim, would be good for kind of the conceptual understanding, because you're talking about the Planck scale, the Planck oscillators, how space is quantized at the Planck scale, and what we might call the Planck field, which is really the 96% of what is missing is, we could say, that field. And 4% of what's observable is the density gradient manifesting through the spin of that field.
Right.
And so if you could just give a conceptual kind of hit on what the Planck field is, so that people, as they go into this module, they have that bit more conceptual understanding of that and the relationship to then the physics.
Yeah. What do you mean by that? You want like a description of the Planck field?
Yeah, like what are the Planck oscillators, and how is this thing organized in such a way that it actually is creating this universal field?
Oh, right. Well, so imagine that, okay, so now we got to introduce the concept of infinite amount of infinities. Nothing stressful. So early mathematicians, some which committed suicide, worked on this. The idea that you have, so there was proofs that were done early on that that there could be an infinite amount of infinities. And you can think like, what is he talking about? Because like, if it's infinite, how can there be more than one? Well, if infinities are quantized, and then you can think, what is he talking about? How can an infinity be quantized, right? It's infinite. But bear with me, right? If an infinite amount of infinities were to exist, they would be quantized, right? So let me explain. So from any boundary in the system you could pick, this is actually what a fractal is, you can find an infinite amount of smaller boundaries in it, right? So the boundary you're looking at is actually, quantized. However, it contains infinity, right? It has infinite amount of subdivisions in it. You can't get to the end of dividing the space, right? If all you're going to do is at one point come out somewhere in the universe, right? Meaning, you can bail out at any scales as you're going in if you're able to travel those scales, right, through the wormhole. And you would end up like on the surface of another universe, or, that is larger than this one, that this one is embedded in that. So every quantized part, right, has all of the scales because they're all embedded within each other. Infinite amounts of infinities. So
that's good.
Yeah. So then if you have that, you can think of that, okay, these infinities or these boundary conditions, these quantization must be in relationship to each other, like harmonics, right? Because they're all interacting. So you can imagine waveforms reverberating through the fractal, wormhole connected network. Think of, a neural network of the universe, the brain of the universe, like, but the whole thing is just like the brain, right? Like it's it's a network of information transferred through these micro wormholes, right? And when you're at one end, you can say, oh, here's one of the fractal division. You might be looking at a Planck, but you might be looking at a proton. You might be looking at an electron. You might be looking at the universe. You don't know, because there's infinite amount of division, but they are all in relationship with each other. So that doesn't, like, the fear in the infinities in physics is that if you have an infinity, you can't write physics anymore. And this shows that no, you can have infinities that are quantized so that you can actually, write physics on the relationship of the harmonics of this whole music of the sphere thing that's going on. And if that model is correct, when you do these math, you should end up with the right measurements, the right constant, the right boundary, right? You should get the right radiuses, the right masses, the right energy level, and all this. So basically, you can take a pixel anywhere in the scale, and from that pixel, you can extrapolate the whole thing. You can figure out the whole thing, because they're all in relationship to each other. So this is literally what we did. We took the proton and we extrapolated what the size of the universe is, what it's its temperature, what is its mass, all the stuff in between, and so and we started at the scale of the Planck, because that's the thing we had measured in the late 1800s. Max Planck, that was showing clearly that was definitely one of the boundary, and that makes one of the pixels. So if you have one of the pixels, remember, you can get the rest, and that's what we did. We found the rest.
Mm-hmm.
So that Planck field gives us all the information we need to understand our universe.
Mm-hmm.
And to understand sub-Planckian and above the universe as well, because you can extrapolate.
Now the Planck field scale, the Planck scale is in terms of the physics that we are doing and the observations of the physical universe, that scale is defining the harmonic quantization and the fractal divisions in part
for our universe.
For our universe, yeah.
Right. But you could think of our universe as being a Planck in a larger one.
Yeah.
Which is a big stretch, because the Planck is very, very teeny. So if our universe is a Planck in a bigger one,
that's a big universe.
Very big universe, right? But let's stretch our mind to that. And you could say, well, the oscillation of our universe, the frequency we measure for the oscillation of our universe, the temperature of our universe, is actually the Planck for that larger universe. Mm-hmm. Right? So each scale can output the other. So with the equation we finished now, that's not in the module yet, because that was not, we hadn't finished that by the time we wrote the module. But now, from any scale, you can output the other scales. So you pick any of the scales, and you can output any other, including the Planck. You'll know at what rate the Planck is oscillating, and what is its radius, what is its mass. You'll know that there's sub-Plancks. You can come up with any of them.
Yeah.
There's a lot of questions about what you mean by Planck fluctuations or vacuum fluctuations and Planck oscillations.
I lost people already there.
Sorry.
I'm so sorry.
No. Actually, that was one of the first questions on the board was, well, what does that mean? Like, is an oscillator going to a high energy state and then transitioning to a lower state? Is that the fluctuation?
Right.
Yeah.
No. So that's one of the issues, is that people think it's easy, including for physicists, to think of fluctuation as like a trace on an oscilloscope, a sine wave, like something that's going you know, like this, which it is, but it's more complex than this. Actually, it's spinning. The oscillation is spinning. What we mean by oscillation is that it's spinning, you know, and this spin, it has a very specific frequency. It has a very specific emission pattern. It has, you know, very specific energy level, right? So you can think of like as spin networks, right? With little, you think of black holes, you know, with these big jets, like on some of the black holes, they're 1 million light years long, right? These big jets like that come out. Half of it, like that's only one pole of the jet is 1 million light year long, right? In quasars and so on. And imagine those as being the wormholes that connects them, right? That eventually makes them into atoms and molecules and all this stuff. But imagine all these spin networks, you know, generating a very specific fundamental resonance frequency, right? So if you think of all the Planck spinning inside the proton, well, it's producing oscillation on the surface. And it's by calculating these oscillations on the surface that I got the right mass, right? How much information from the little Planck inside are going through the boundary when the boundary, you know, caves, and how much are going, you know, in when the boundary bulges, or the other way around, like depending on how you think about it. But, you know, so that, and that give the right answer for the mass. That is the energy that, so basically what I discovered is we knew space was oscillating. It's called quantum vacuum fluctuations, right? We knew it was oscillating. We just thought it was completely random, right? And what this is showing is no, this region of coherent, you know, collective behavior. And that's why, and in these regions, we call it matter, right? So I hope it's clearer for people. Yeah, oscillation. So you can think of the field like oscillating globally, right? But you can think of the little ones oscillating independently as well. So that it's a relationship about the collective behavior and the singular behavior at the boundary that you're looking at. And that gives you the right mass, right? I hope that clarifies.
You know, that was something so interesting though, because that gives you the solution to the mass. You know, part of it is the information exchange that's occurring on the inside of the black hole, in this case, like a proton to the outside. And I just remember about 6 months after you had published that, Stephen Hawking came out with his statement that black holes are actually gray. We wrote an article, Stephen Hawking goes gray.
Yes.
And part of that was saying that the information is coming across that entire horizon. Yeah.
Yes. It's not just completely black. There is some electromagnetic oscillation that are emitted by the black hole. Absolutely. Yeah. And people think, you know, this is a misconception about a black hole. It's like people think everything that goes close to a black hole just gets sucked in and dies. And actually very little can fall into a black hole. It's the problem that happened is that the math we first wrote didn't have spin for a very long time. So Schwarzschild solution didn't include spin for a very long time. So they were visualizing a black hole that's still, right? So of course, a black hole that's still has huge gravitational force, and anything that gets closer will fall in, right? No doubt about it. But when you add the spin, which is the current Newman solution, and you add the observation we see, like galaxies that orbit black holes, right? You find that actually, you know, a black hole event horizon is spinning at near the speed of light. And for a particle to fall in, it has to be exactly in the right angle, exactly at the right place, which is the poles. you know, to actually fall in. But at the equator, the thing is producing, you know, centrifugal forces that are massive, that overcome the gravitational force, produce a balance, you know, orbital. And that's exactly what we see. We see immense stars, you know, millions and millions and billions of times bigger than the sun, are orbiting the center of galaxies just happily, you know, very close to the horizon. And you know, the standard model has very large difficulty accommodating for that, mostly because they have this problem with dark matter, and they don't understand that the vacuum that's spinning, not just the objects, right? And when you add that with the centrifugal forces and the centripetal forces, then you get, you know, what galaxies can look like without the need for dark matter.
Great. Let's see. We got lots of questions here, and William and Olivier, if you see some more, I know you, William, just asked one. That would be great to pull some out. This one, I don't know, maybe it's a little too technical, but we'll go for it. It might be more challenging for people not yet familiar with the theory, but it's from Randy Langle, and he's asking about he says, when is it appropriate to use the surface to volume ratio of a black hole, a proton, any entity? And when should the volume to surface ratio be used? At what size entity do we stop using the former ratio in calculations and start using the latter ratio? So this is maybe what you can do is just describe a little bit about the ratio between the surface, like of a proton, and the volume or of any black hole, and what those ratios are defining, and then how that translates across the scales.
Right. So there is the ratio between the surface and the volume. So you have surface to volume interaction, right? And that ratio specifically, so it's very simple equation, the number of Plancks on the surface to the number of Plancks in the volume gives you a ratio that if you multiply that ratio by the Planck mass, so the, you know, the particle that's making the thing, right? Then you get the mass of the particle. So, you know, this gives you a very clear picture, but can you actually, he might be alluding to the fact that the equation, when you apply it to the cosmological scale, goes 1 over.
That's what it's talking about, you know. So if you're doing, you know, Cygnus X1, you know, it's the volume over the surface. Asking at what point do you have a transition where it's surface over the volume?
Right, at the proton scale, you have a transition, well, actually, at the electron scale as well, you know, the transition is there, and that's because you're changing the metrical space, because your frame of reference has just changed from being inside the black hole, calculating the mass of other black holes, right? And from being outside the black hole, calculating the mass of black hole, you know, that are in, you know, smaller than you, right? So and those are still inside the larger black holes. However, in this case, your metric, your frame of reference has changed. And so this is known in Einstein field equations as the crossing of the event horizon. That is when, okay, so like a little bit background. When Einstein's equations describe the surface of a black hole, it describes it in what is called, you know, parallel transport coordinates, in which you have, you know, like a tree space, like 3 vectors of space, right? and 1 vector of time, so 4 space. And imagine those being a point on the surface of the geodesic of the object, of the surface, right? And imagine that these 4 points are going around, right? And so the equation tells you, you know, the gravitational force and all this based on these 4 vectors going around, right? Except that we know that when these vectors fall into the black hole, when they go across the event horizon, those end up flipping, so that the space vectors become time vectors. And here I'm gonna like put a little parenthesis. Time is not what you think it is. Okay, we'll have to go back to it. Okay, and then so the time vortex become a space vortex. So that means it's like 1/. It's like it flips, right? The space vectors become time vectors, the time vectors become space. So that this flip happens, you know, because, and so basically now you have to flip the equation because you're describing something that's smaller than you, right? Something that's like inside of you, if you'd like, or inside the frame of reference that you are observing. You're inside the frame, even if the frame of reference is not a person. Let's just say it's a frame, right? It's either the outside frame, or now you're describing what makes up the frame, right? So now you have to flip the equation, and then you flip the equation. So now it's the information from the outside coming in, right? The volume, right? So all of a sudden it's the, I'm sorry, instead of the volume over the surface, now it's the surface over the volume, you know, which is the information going into the system, going into the frame of reference, because you're using the frame of reference to define the frame of reference. It's like the hand drawing the hand, right? So now you got to flip the equation. And in the equations we are writing right now, we're finding that actually we can define alpha, beta, gamma, like all these fractal structures that gives us the good answer for all the scaling. When we do that, basically we're just flipping the relationship between the radiuses and the mass to get the value. So it's like the universe is doing one of these. And this is why the sun flips its poles every 11 years. This is why the earth has flipped its poles a bunch of times. There's a 1/x value in the structure of space. And it's part of, because you have information from the inside going out, and you have information from the outside going in.
Now, in regards to the proton, my understanding is that that one way of correlating that ratio defines the holographic mass and the relationship to its relationship to the entire universe, and the other, when you flip it around, correlates to the rest mass, to the very much smaller value that is typically measured and calculated and defined.
Very good. It's a very good point to add this. It's a little more complex for people to understand, but let's think about it. Basically, that's very good, Marshall, that you mentioned that, because basically you have the rest mass when the ratio is flipped relative to the cosmological scale, right? You have the rest mass, the proton, very precisely, and its radius and all this. And then when you flip that ratio on the proton, you get the gravitational force that the proton is producing, that I was talking about. That's very, very strong, meaning it makes the proton a black hole. And you see that like the energy of the system. So basically you can say, when we measure the proton's rest mass, we're actually measuring the proton as if it wasn't spinning, right? Rest mass, right? But when you add the spin, you realize it's a black hole, and it has the gravitational effect of a black hole, which we call the strong force. And it all adds up nicely. So then you understand it's not just one neither, because each boundary is in relationship with the outside and the inside, right? So the same flipperoo happens at all the scale to give you gravity, electromagnetic fields, and all this stuff we see. So it all kind of works out. It doesn't just kind of works out, actually, it works out extremely precisely. I should be more specific.
So it's really all an interplay of this ratio, really across all scales, we could say. The inside, outside, volume to surface ratio.
Right. It's all geometry, which Einstein knew. And he said, you know, when we find the unification theory, it's going to be straight algebra, and it most likely, you know, geometry and algebra. And, you know, it's probably going to be much more simple than we thought. And it is. I mean, you know, I mean, it can have, and it will have much more complex math attached to it, but the core is very, very clear and simple.
Yeah. All right. William or Olivier, do you see a question you think you'd like to go to next?
Olivier, let's ask a question, Olivier, with your beautiful French accent.
Yeah, it was more a remark, maybe. It's nice because with this model, with the Planck plasma, considering the Planck's plasma and the toroidal structure of the vacuum, we find, just solving Navier-Stokes equation, we find the holographic solution. The first presentation of the holographic solution was in terms of entropy and information transfer. And it's very nice to see that we can find the exact same result just with a mechanical model, considering a fluid, the plasma fluid dynamic, and solving Navier-Stokes equation.
Yeah, that's remarkable, yeah. Actually. Yeah, keep going. What were you going to say?
Oh, just to complete the view from the description you gave, from the oscillatory part.
You want to explain what the Navier-Stokes equations are?
Oh yeah, the Navier-Stokes equation were these old equations that are very difficult to solve because they are not linear, and they are pretty much used everywhere in solving fluid dynamics from the cosmological scale, understanding the weather on Jupiter, or solving how you get water in your house. So these equations are pretty everywhere, and is using like all Newton laws, and they are working pretty well, even if they are written in a difficult way, difficult mathematics to be solved nicely right now with the tools we currently have.
You're working on the niceness.
Yeah.
Making it simpler.
Yeah, they're biting a little bit in the complexity. They give the right answer, we know, but we're trying to clean it up. But it's remarkable that we can describe it in fluid dynamics so straightforward from mechanics, which are very fundamental. That includes viscosity and thermodynamics, right?
Yeah, and the really interesting part, it's like it gives information about what you often talk about. It's the gradient and the speed gradient that is at the origin of the spin of everything and of the mass. And this is a question that people are asking about the origin of spin. And maybe you can expand on this notion of gradient of speed creating this spin and everything.
Right. Well, you have, so imagine that you have a density gradient. A common density gradient we have that everybody can experience is a density gradient in the air, right? So they're related to temperature, right? So a temperature gradient you could think of a temperature gradient in the air, you know, like cooler air on the surface of the ocean, and you know, hotter air in the ionosphere, or even lower in the atmosphere, that's interacting with the cooler air, can all of a sudden start moving the air around. The air starts moving around because the cooler air is trying to go down, and you know, the hotter air is trying to rise, and so it changes. Or you can think about it the other way, like and it's a small gradient, about 3-degree difference between the surface of the ocean and the air, and all of a sudden the particles of air are starting to move. They're picking up more and more fluids as they move. Things are getting hotter and colder in the middle, and when that happens, it starts spinning, and now the center gets really, really cold, and the outskirt gets really, really warm, and it starts carrying millions of tons of water, and it starts dumping huge amount of electrical discharge all over the place. We call it a hurricane, and it's going about 300 miles, you know, 100 and some miles an hour, and you know, and it's picking up, you know, massive amount of material. And when we look from space at the hurricanes, we see jets that come out that are antimatter jets. Did you know that hurricanes produce antimatter jet? You know, I had to teach it to my young friend Olivier. He didn't quite believe me when I told him, because you know, those are high energy physics that's expected in very high energy system. You know, that means there's gamma emission, because antimatter jets are the result of gamma particle interacting with anti-gamma particle and producing, you know, gamma ray emission, you know, or interaction between matter and antimatter. And so this is very, you know, amazing about hurricanes and tornadoes. But basically, think of it as the density of the vacuum is a little smaller on the universal size than on the atomic size. Well, it's not just a little smaller. It's very, very different in terms of density. So you have, you know, a high gradient. And so you can imagine, if this infinite amount of scales, it's either getting denser or it's getting less dense. And, you know, the less dense is going towards the denser, and the denser to the less dense. And so the whole thing is spinning into infinity, from infinitely big to infinitely small. So this gradient is what's driving the spin, and the spin is what's producing the coherent behavior in the local area of space that we call matter. You know, and all the spins in between, like the galaxies, the clusters, the superclusters. So basically, that's all a gradient of spin going towards infinitely small, or going towards infinitely fast, and going towards infinitely slow, if you'd like to think, as you're going into the universe. But slow and fast is not quite accurate, because it depends how you're defining spin, because you can think of a point on the surface of the universe going around, right, in a circle that's the size of the universe. Well, even if the universe is going really slow, if you take the frame of reference of that point on the surface, it's going really, really fast, you know, to go around the universe. It's traversing a lot of distance with very little movement of the universe, right? So actually, you know, it's best to think of it in density gradient. Don't you think, Olivier?
Yeah, and there are different gradients. There is the density gradient and the speed gradient that can be directly linked to gravity.
Right. And yeah, so you have a gravity gradient, and then you have, you know, a temperature gradient, right? And so on. So all these things should come together, and in the equations we wrote lately, they do. So it's really good. It gives, somebody's mentioning consciousness. Yeah, consciousness is part of that whole gradient thing. So you know, more gradient you can produce in your consciousness, more information can flow through, faster it can spin, right? So how would you create a deeper gradient or like a stronger gradient? You would have to go inside, right? You would have to like go into the singularity of your existence, like going into the frame of reference. And as you go deeper and deeper in there, so as you integrate matter at the deeper and deeper level, you actually increase the amount of information going through the system. So you actually can control the density gradient of your existence if you choose to do so. Otherwise, it just runs on the average density gradient, because it's remember, it's spin networks. So you know the network is, you know, can be spinning at a certain speed. It has a tendency to entrain all the other oscillator to the same speed. So you know you have to depart from the natural resonance frequency of a set of information on the surface somewhat to bring it to another level if you're trying to. So that takes there's a little entropy there.
So Nassim, there's a question here. It says in module 4, says that the reaction making the universe to change its size, to expand, is the universe accumulating information. The expansion is the accumulation of information. You were just actually kind of alluding to that there as well. So where does this information come from? What is information? Where does it come from? How is it accumulating and expanding?
Well, you know, formally information in physics could be described as the position, the angular momentum of a particle or its energy level. Basically, you can say, okay, I'm going to identify this point. Let's say it's a Planck, right? Which is what the holographic principle first initially did. They say, okay, you know, a Planck is one bit of information. What do they mean by that? It's like a Planck is defined. So this is, again, let's take it out of the way it was first interpreted and bring it to, you know, what I was talking about, the infinite amount of infinities. So imagine that, okay, each point, okay, so it's all one, right? Because they're all embedded within each other, but each point you define, you can see would have a specific relationship to the rest of all the other points, to infinite universes, right? It would be individualized. It would at any scale you pick, it would be the only point that's observing the universe from that coordinates in space-time. So you can think of each point as literally one bit of information that's differentiated from any other bit in the system. It doesn't mean that they're not connected, that are not in contact with each other. It's that each hub of the network is going to send a different set of information to the whole. So each infinities is individualized, right, from the whole. And that's the illusion that, you know, at first can confuse a human being and think that they're separate. Because we're all humans, but we all look different. We all look different because we all get different sets of information, because we're all looking from a different coordinate in space-time. Nobody sees the same object. We only see different aspects of the same object, right? And interpret it that way, right? So basically, you can think of it as the way your consciousness, you know, is able to inform the universe, is going to produce a feedback that's going to inform your physical body, so that you're going to look different than me, and that then Olivier, then William, and you know, we're all gonna agree we're humans. However, we're all gonna be different. Like every snowflake is different. Every, you know, every digital imprint is different. Every iris is different. So basically, all this information. What was the question again? I got lost.
Well, you were just starting with what is the information, and
Yeah.
then how is it accumulating to increase the
All right.
information of the universe?
Right. So basically, all the information flow of all the points in the universe, you know, interact to produce the thing we call the universe, the reality that we see. So when so the universe is literally learning. Well, if the universe is learning, that means it needs more space to put the information. If each bit is a Planck, it needs to have more surface. It needs to have more space, and so it grows, right? And so, but they are growing in relationship to each other. So everything is as if it didn't grow, right? Or, you know, there's relationship between each scale that can be a little, you know, have a gradient between them in the growth as well. So you see growth, you know, in certain epoch, you see collapse in other epoch, like, you know, a star gets bigger, and then eventually explodes. And then we see the black hole that was in the middle and so on. So basically, you know, you see cycles of information exchange that is constantly happening as the system is learning about itself, including you, right? So, you know, a star that goes supernova and a black hole that's left in the middle didn't die. It just went through a cycle, right, of learning, and then propagating that learning, like you make children, so that there's more surface of humans on the surface of the universe, or on the volume of the universe. So there's more information that can be transmitted to the universe through those little guys, right? So you've propagated the information, and it's very specific information that has to do with your ancestry and your genes and all this stuff. I mean it literally, right? I mean, that's how a society grows, right? There's kids being made, and generations, and hopefully some of the information stays coherent through this generation, and the system learns to become more and more evolved. Does that make sense?
Mm-hmm. Yes, it does. Great.
It takes a while to integrate all this. You know, I'm giving you a lot of details. I'm just trying to fill it in for people, because I'm excited as well because of the math I'm writing right now, and it's coming together.
Well, it's good to convey the conceptual side of all this, so that the whole picture can get more and more formulated and understood. Because it's when you understand the whole picture, the quantization, the gradients, the you know, the different forces, and how they're really just attributes of the same dynamics, and the information and the expansion and the input outputs and all of it are really all just the same thing. Right. And when you understand the concept of that, and you start to see all these different ways of looking at it, you start to see, oh, it's actually quite simple underlying what looks very, very complex and can go into incredible complexity. Underlying that is actually a fairly simple model.
Exactly, because there's only one thing.
Yeah, exactly. There's only one thing, and it's geometric and you know, coherently organized and harmonically structured. You know, once you just start to get that whole picture, when you then read through module 4 and just look at the whole of what's being presented from that perspective, it starts to get easier to see how, oh, this is how it's all working. You know, it's really much simpler than it seems.
Yeah, so, even further, if you allow the information to, you know, like just to be open to it, you know, that doesn't mean you lose your critical capacity, but just to let it come in and flow in and kind of try it on. You know, it's almost like going in your closet and trying it on and looking at yourself in the mirror. If you actually do this with this information, you'll start to feel it. You'll start to feel it. This is how I feel anyway. I can't tell.
A lot of people do feel it here.
but I've got that reflection over the last 30 years many times, that people, you know, go through transformation when it clicks and they get it and they start feeling it. It's like, whoa, you know, this is another level of like, because now you start to feel like you can, oh, I can control this information. I can do things with it. You know, it's not just an esoteric thing going on. It's actually, so I'm feeling the mana, you know, I'm feeling the vacuum, you know, yeah.
Great. William, do you see a question you want to bring in?
Yeah, you know, I was also thinking, you know, as Nassim was describing that, you know, he was describing how systems evolve and how that's a function of the space memory, the information being coded on the surface horizons. And, you know, one of the things that we explore in the Unified Space Memory Network paper is how that also explains evolution, even in the biological sciences. So, you know, that's the mechanism explaining directed evolution. You know, so you kind of had this theory where it's saying that you have random mutagenesis, and nature's just trying a whole bunch of different combinations until it serendipitously hits the right one, and then you get a useful feature in an organism that evolves. But you know, one of the things we show in the USM paper is that, well, for some of these biological things that are so complex, like a single protein, to try all the combinations would take like hundreds of billions of years longer than the universe has been around. So it's like that just does not, it's not a sufficient explanation that it's just like randomly hitting on these things. But if you have a feedback system, feed forward system, that's evolution, you can have it directed, you know, so that it's self-organizing, but it's informed via that feedback feed forward structure that's in the space-time metric itself. So it actually explains biological evolution too, which is, for me, really exciting.
Yeah, it's remarkable. You can even, we wrote the equation now with Olivier so that you can even go down to really just Brownian motions in the Planck plasma, right? And then output Brownian motions, for people that don't know, is something Einstein worked on very specifically, you know, which is the movement of particles in a gas, for instance, you know. And so if you're talking about plasma, which is 99.8 or 9% of the universe, you know, you're talking about Brownian motions. And so basically we apply, which is particle to particle oscillation, how they behave, you know, if you take two particles in a gas. And then, you know, we extrapolated that to the Planck field, like two Plancks interacting, and wrote and looked at what the equation would output, and it outputted exactly the holographic mass solution. And then, you know, and that was just remarkable. So you can actually, and these are thermodynamic and viscosity equations, right, as well. So you can actually output like how the viscosity of space-time eventually like produces, you know, biological viscosity, if you'd like. You know, with a very specific thermodynamic signature, you know, like, you know, we're burning at almost 100 Fahrenheit continuously, you know, and if that thermodynamic signature changes by a few degrees, we're in deep trouble.
Yeah.
You know, it's got to maintain very specifically that spin rate, that temperature in the vacuum structure, right? So it's remarkable. You can even describe it as Olivier was saying, mechanically.
Is it the equations that you and Olivier wrote for that Brownian motion, aren't they related to the same equations you'd use to explain the crystallization of water? Is that correct?
Yeah, there's a possible link there.
Okay.
Called the Lib's constant that was mentioned to us by Alan Green, I believe, and we started looking into it. We haven't finished this part, but yes, there is a direct relationship that can be applied, because both are thermodynamic equations, and they are, you know, very much related in terms of the way they are written. So we know we can apply one on the other, but we haven't finished that work. But yeah, and that will be the nail in the well, I don't want to call it the coffin, especially now these days. So I'm going to call it, you know, I'm going to call it the cherry on the sundae. It's much better. So the cherry on the sundae is that we'll be able to describe basically the structure of space-time becoming more crystalline at certain scales, right, and undergoing phase transition, and that would eventually lead to liquid water, you know, like a liquid crystal water, and you know, and that, because we can see a direct relationship when water turns into a crystal to what our equation is telling us about the Planck plasma. So as soon as we finish this, which just we didn't have time to address it, we know it fits. We're gonna be able to like explain how water becomes coherent with, you know, with minerals, you know, using like how the crystalline structure and phase transition of water, right, from cold to hot, right, basically, right, the Planck field being almost at 0 Kelvin, at you know, at large scale, not the Planck itself, and you know, getting warmer, you know, as it as the crystal melts, you know, into biology, if you like. That's why biology looks so messy compared to, you know,
crystals.
The crystals, you know. Yeah.
Well, let's do one final question here, kind of bumping this out into the context of relevance in our planet here, our human experience. It's a question from a longtime friend, Mitty Berry. And she's asking, one of the big challenges in implementing radical solutions in society's challenges historically has been the issue of how to scale up practical inventions that are shown to work in small scale experiments. Can applying the understanding and implications of unified science help us facilitate bringing solutions to scale?
Like in terms of technology?
Yeah, I think in solutions to, you know, the kinds of challenges we're facing in the world right now, technologically, right, even socially, you know, by understanding as we talk, the worldview shift. But
yeah, I wanted precision because there's one of the sections of this module that's called, you know, resolving, I think it's called resolving the hierarchy problem, which has to do with scale as well. But I think it's more general, the question. So
the scaled up solutions from a small scale in the laboratory to something that could really serve the world.
Right. Absolutely. I mean, this is very much the goal of the whole operation. If we understand the universe from its very fundamental perspective, and certainly if we understand how gravity is not just a curvature in some, Minkowski space, but it's actually a curvature in quantum fluctuation, then it's clear that there's a path to gravity control, energy production, just entering the universal net, basically entering the gradient, letting the gradient of the universe run your device instead of trying to extract the energy after it's gone through the gradient. Meaning, like, imagine a gradient that's going from the universe to subatomic particle. Imagine that as a river flow, right? And we're on the edge of the river, just picking up what's on the other side, the event horizon, right? Just the fluff, on the edge of the river. We're picking up that, and we're having a hell of a time to pick it up because it's, unruly and we don't have any control over it. Meaning, like, let's say we want to produce energy, we have to wait for a few billion years that plants under the ground get compressed into, like, oil that we pump out, that, or we have to, wait for material like nuclear material to form, or more to our analogy, we have to put a turbine into a river, right, and spin it. And, most of the force is not utilized. Like, gravity is spinning your wheel, but it's not efficient at all. Like, if you could pick up all of the gravity, then you could power, cities, universes, planets, social structures. Like, if you can put your wheel, your turbine, instead of putting it in the river, you put it in the river of the universe. Right now, now the thing is spinning like a bat out of hell, right? Like, it's going really hard, and you don't have to build a huge cement dam to get some pressure in your lake to get the water to come down, because the water is already running. The thing is running, right? It's it's already, like, and just like the river is running before you put the dam, you just got to figure out how to make a little division. Just make a little division in the space to create a little bit of a gradient, and boom, the gradient of space-time is flowing your way, and you can direct it, you can, do all kinds of things with it, right? You can direct the flow in a certain way to produce thrust. You can, and the thrust can be up, so, it opens the door to everything that the world is able to get, that the world deserves, that the universe is what we are, and we are the universe. More we understand who we are, more our technology allows us to go and explore the universe. And that is a very clear linear relationship that we see in all of our evolution, from cavemen that couldn't go very far from their cave to people now able to go across the world in a few hours. Our evolution includes our capacity to go further.
Yeah, exactly. Yeah, so that's a beautiful description of the application of the principles and the understanding of the dynamics of this unified physics model, then being tapped into this current flow that's a gradient across all scales. When we understand what it is, what it's made of, how it's dynamically interacting, what the geometric and harmonic ratios are that it's organizing by, then we can apply that and scale it up to, for example, solve our energy problem in the world, and to do away with the problematic sources of energy, and transportational
Resources.
modes and all
Yeah.
that, and all the resources.
Yeah,
And it will just clean up and balance our
everything.
everything exactly
Yeah.
in this world.
Yeah,
So-
I mean, imagine that, you know, in this quarantine, people are noticing, oh my God, animals are coming back in the cities, and like,
Mhm.
you know, things are turning green again, and like, oh wow, the pollution levels, like, you know, I saw pictures of the channels in Venezia, you
Yeah.
know, the channels are cleaning up, and like, you know, everything, like the pollution, like as soon as we stop burning carbons and
Yeah.
we access energy, almost infinite amount of energy, everything will change, including our capacity, if we're controlling gravitational field, to literally take our civilization off the surface of the planet, which
Mhm.
is a good nest to start a civilization, but it's not, you know, sustainable over a long period of time. The bird have to learn to fly, and learning to fly means not burning fossil fuel, but learning how gravity works and work with it, you know, be part of the gradient. And then when we take ourselves off the surface will recuperate very fast.
We'll have a beautiful garden planet to come visit.
That's right.
Yeah.
That's
And
the
a whole
garden.
vast galaxy and universe to explore, which is pretty darn exciting. Really, when
Yeah.
you think about it.
Last count was 40 billion planets that were, you know, habitable in the galaxy alone. So,
Yeah.
you know, let's go and check out some
Well,
bar on the other side of the universe.
First step is to get our act together here, and that's what this is all about.
Yeah.
And
Yeah,
that's why-
exactly. There's
that's
bouncers at the bar entrance. They don't let you in if you're
That's right.
just a cowboy coming in. I mean, nothing against cowboy. I
Yeah.
love country music, actually.
Metaphorically
You
speaking.
know, it's best not to shoot, like, you know.
Well, great. Thank you for that. And we're at our 2-hour mark for today. And thank you for everybody for being here and for the questions today. As usual, we just only can get to a few relative to how many come in.
Yeah,
but you can see
Marshall,
it's
about that, maybe we got more than 100 questions and we didn't answer all of that. And people can ask their question on the forum, and
Yes.
we will be more than happy to answer to all these questions.
That's a great point. Yes, put your questions in the forum inside the course there, and also in the course in the website is the store, and you can go there, and we have various membership levels that you can come in and register with to support the foundation. And this 6-week series we're doing now for free would become then part of what's offered in the ongoing monthly offerings of the course itself, where we have the monthly live with Nassim and faculty Q&A, and that's part of the membership program. So you can check that out. And we actually bumped up people. It's so wonderful. People are asking, it's the base level is $5 a month, and people said, I'd like to actually contribute more. So we had a good problem of having to add more membership levels at higher levels so people could actually contribute monthly at a level they really felt they wanted to.
Yeah, and it's so important. Yeah, I'm sorry. And it's so important. It makes such a big difference for us. You know, like we're going, yeah, it makes all the difference. We're going as hard as we can with a really small team, and our budgets are very restricted right now, specifically. And so it makes a huge difference. And thank you so much for becoming members and doing this and taking the course. I love you guys, and thank you for the love. We are all feeling it.
Yes, we are. That we are. And tomorrow with Olivier, we have the second in this 6-week series in French, in the French delegate or Unified Science program. And so that's, again, at 12 noon Pacific time. If you are French speaking and you'd like to participate in that, well, that's happening tomorrow, and you can register for that through I guess through the website, the French program website. Is that right, Olivier?
Yeah, exactly. And
Okay.
most probably Nassim would jump in at some point.
Yes.
You never know. I might come out of a wormhole just like that.
Fortunately, Nassim speaks French, so that it helps.
That helps. Yeah.
And I'll be on there for a part of it tomorrow as well, because I helped to write module 2, and we'll be discussing module 2 and the French program tomorrow. So
Fantastic.
great. Thank you, everybody, for coming today. We had over 1,000 people on Zoom, and I don't know how many on Facebook Live, but we're so excited to have you all here. So grateful that you're participating. All your comments are so wonderful, that you're getting so much from the program and from these discussions, and that means everything to us as well. So
Thank you so much. May the vacuum be with you. Stay healthy, and see you next week.
yes, we'll see you next week. Same time. Okay. Be well,
All right.
everybody.
Thank
Bye.
you so much. Thank you, everybody. Thank you, all of you.